Hi everybody, welcome back. This is lesson 3, part 1. What I'm going to do right now is take you through a enhanced version of the lesson 2 sketch where I've added a lot more functionality, including making the code read and write to actual I/O pins of the Arduino. So without diving into what we've already done, you know how to read serial, you know how to respond, you know how to look at strings. If you don't, then please watch lesson 1 and 2 before you watch this one, and it'll still be here when you come back. Anyway, so I'm not going to go into how all that other stuff works. I'm going to dive right in and start showing you what this new sketch does before I actually show you how to improve it. I've deliberately written it in a way that is typical for most newcomers to the C programming and to the Arduino world, and this would be the same for MSP 430s and even people programming on a Raspberry Pi, because up until now nothing has really changed too much as far as how you would do anything. The only thing that distinguishes this sketch from anything running on an MSP 430 or on a Raspberry Pi is the I/O that we're going to now start talking to. If you put a LED or an oscilloscope or something onto the output pins, or a pot on one of the analog pins, you could actually vary it. But for now, the pins will be getting turned on and off. You can read from the analog port. It'll just read whatever random value is floating around on them, and the PWM outputs will start putting out a pulse width modulated signal that you could connect to an LED or something like that and vary the brightness of it. I'm not going to talk about how you connect those things up to those particular devices right now. There are plenty of blogs and forum entries both on this forum and on the Arduino's own forum that tells you how to connect an LED up to a PWM output or something like that. So anyway, let's get into the program. So at the very beginning, still, as you can see, lots of comments. The first main thing that you'll find different here is that I've put an extra define that says command delimiters, and there is a string of different delimiters here. You'll see what they're for later. I've also defined all the different pins that I'm going to be using on the input and output routines. The reason I've done this is because it's a real pain in the butt to try and remember which pin is D2, which pin is PWM1, and things like that. So by defining a friendly name for it, like D0, 1, 2, 3, 4, 5, 6, 7, and then assigning the value of the pins next to it, all the way through your code, you can now start talking about just D4, and in the code you'll just write D4. When it actually compiles, it will get replaced with 7 in the case of D4. So the same goes for the PWM outputs. There's two defines here for the max PWM value of 1023, which is, if you know at the analog ports, that's the highest value you can output with an analog write, and the minimum value of being 0. You'll see where I'll use this later on. The other thing that's in here as a define is a simple bit of math, which is the analog to volts. What this will be used for later on is to convert the reading when we input from an analog read into an actual voltage between 0 and 5 volts. The default reference for an Arduino Uno and all of the other Arduinos is typically the 5-volt rail that's on the microprocessor. So that means that the analog inputs will read 0 for no volts in, and will scale linearly up to 5-volt input, giving you a reading of 1023. So this just gives us a number that we can use later on, and you'll see when we run the sketches that can just tell you the actual voltage on the input pin, not just the digital value. The next part, you've seen this before, the character buffer, so I'm not going to explain that anymore. Serial index, you've also seen before. So now in the setup, what we've got here is we've added the standard commands. There are better ways of doing this, but this is typically how people do it, and I'm not going to be improving on it inside this sketch. But basically I'm just going for the D0 to D7, the PWMs. They're all output, so I'm setting the pin modes to outputs for those. The default for everything else for the analogs is input anyway, so I don't need to do anything there. Again, initialize the serial port. I've expanded the friendly hello message on this one, so it will account for the extra functionality that we have, and it's just extra serial prints. The loop for main, as you can see here, has not changed one little bit from the previous lesson. Do command has now been modified a little bit, and what we have here is we're using character pointer for command. We have a character pointer for a parameter, and we have an integer for an analog value. What these are going to be used for is when we read something that's come in from the serial port, we're actually going to start stripping it apart. In the previous lessons, all we did was look at the string in its entirety and just simply see if we had a match. Now we're going to be able to use those delimiter strings. If you remember what we had up the top here, where is it? There we go. A bar, a comma, a dot, a dash, or a space. These are all able to be used to separate a command from a parameter and things like that. So in this example, we're just going to accept two parameters, the command itself and a parameter separated by one of those delimiters. If that parameter is able to be converted to a numeric value, we will also set a value into analog val. So just going through here. Now again, I'm not going to explain the details of what each of these commands do. You can go Google them and look them up easy enough yourself, but I will give a very brief description. So what Tratak does is it finds tokens inside a string, and it will split the string up to that token. So what's happening here is command, which is one of our first parameters we have up here, is a character pointer, which is like a character array, but it's just a pointer to it, is going to be populated with whatever came in on the buffer up to the first instance of one of the delimiters. The parameter is going to be filled with whatever may be after that delimiter up to the next delimiter. Now you can add multiple parameters and just keep adding statements like this one, which will keep then pulling the next and the next in and things, but in our case we're just looking for one more. The difference between the two here is that the first one, when you call Tratak, you give it the command buffer as the string for the input source to it. The second time you call Tratak, you give it null, indicating to continue working through the buffer that you were given before. Quick word of warning with Tratak, it does not nest, so be aware of that fact if you try to do different things with it and things start going funny. Just look for nesting, it doesn't support it. So okay, so now we have potentially a command and a parameter that's been stripped out with Tratak. The next thing we're going to do, if you remember, is we're going to check to see if it is numeric. We're going to set an analog value. So what I'm doing here is our out parameter is being set with a 1 or a 0 based on the return from an isNumeric function. Now I'm just going to quickly scan down to isNumeric. I actually put it in here. Here we go. So all it does is take an array of characters, and it will scan through it and check each one to see if it is a digit. And if it is, it will just loop through and eventually return a 1. If it isn't, it'll return a 0. That's all very, very simple, and it gets the job done. So okay. There are functions that are in better versions of C and things that allow you to do this, but in our case this is a simple way of writing it and getting it in without pulling in any additional libraries. Alright, so we've just called isNumeric. If it is numeric, out parameter gets set to 1. If it isn't, it gets set to 0. So you can just use this as a Boolean true false now. So if it is a 1, meaning we've got a numeric value, then we assign the numeric value to the analog val, which we declared higher up. hy is a simple function that will convert an ASCII string into an integer, and that's all we're supporting for this. And we just give it the parameter if there is one from before. If there is no parameter, then isNumeric will also return an error. Oh, sorry, a false statement. Right, so assuming that we do have a correct parameter, what we're also doing here is we're verifying whether that parameter is within the range that we set for PWMs, okay, which is 0 to 1023. Sorry, I have a mistake in this. The PWMs are not 1023, they're 255. So just a quick change to this. This is for analog, is 1023 for reading. So PWMs are 255 maximum value. Sorry about that. Alright, so that'll, now you see the benefit of having these declares. I just go and change it in one place and it'll be effective wherever I've used the max value, which in this case is only 2 of them here. Sorry, 1 right here. But if it was a more complex program, it could be in multiple places. So what I'm saying here is if the analog value that I'm trying to output to the PWM is greater than the range that I've set, then it's going to say that there is no, it's going to change the output parameter to be false again, indicating that it's invalid. So we'll just ignore it. So from lesson 2, you'll already be aware of how structcomp works. I've converted all of the compares now for the strings to use structcomp, because in lesson 2 we went through different variations of using string comparisons, and we came to the conclusion that structcomp is the best one to use. It does an exact match, even though you have to have the equals 0 at the end of it. So some of these commands are exactly as they were before in the lesson 2. So hello back at you, goodbye back at you, do something like what. Web 1 was there where it outputted a string. Now what I've done now is added a few extra ones. The reason for this is they're very slight variations of a theme for the same ones, but I wanted to use up program space and also use up RAM. Now for what I'm doing here, it's hard to see why I'd be using RAM, but I'll explain that in a moment. So I've just added extra Web 1, Web 2, Web 3, Web 4, Web 5. They're almost identical to each other, which is quite typical with HTML. You know, you'd have a header area, and the only bit that's really changing is in this body of the page, and then the rest would be the same as well. So now what I've also done is added the ability to read from the analog port. So adding extra else if structcomp commands. Now I've got analog 0. It'll read from analog A0 and also return the volts. Remember we had that little function in the define which got us our analog to volts, which was the 1023 being divided into 5. And I've repeated this for each of the analog inputs, so it's A0 through A5 here. They're all the same. Digital 0 through digital 7 are all the same, and what they're doing is they're allowing you to output to the digital port. If you've said something like digital 7 space 5, it really doesn't matter what it is. It'll just invert the output of the port. So if it was a 0, it'll make it a 1. If it's a 1, it'll make it a 0. I'm not actually using the value except to indicate to toggle it in this particular example. We will get more specific later on in the second part of the video. Now we've got some PWMs. This is again just adding more and more commands, and again what we're doing is this time we're taking the value, but what we're looking at is this out parameter. Remember above we checked the out parameter to true or false based on whether we had a numeric value and whether its range was within the range of an analog output port. So in this case that's not 255. If it was greater than that, this would be false, and therefore it would not execute any of these PWM commands. If it is within the range of 0 to 255, it will execute them, and again it's going to tell me what it's going to output to the back to the serial port what was sent in, and then it'll also set the analog write to the value that we input from the serial port. And that's the same for all of the PWMs as well, up to PWM5. And then, as before, we've got this catch-all that says, I don't understand you. And it will simply drop to this if you give it a command that's not recognized. Debug is the same as it was before, except that I'm now also outputting the extra parameter that was sent in if it exists, only if it exists. We still print the free RAM. Check serial has not changed at all. Free RAM has not changed at all. So you can see here the only thing that I have done that is different is added extra commands and extra responses to those commands into this. So you would think that there is not much here that would be chewing up all of the memory. But if I just quickly load up the previous lesson 2, and run this one just so that you can see the difference. Alright, it's 3.254K in size, and if we just fire up the console on it, let's wait for that to come up. Came up on the other screen. Sorry about that. Let me just go grab it. Okay, so if I just now say hello on this previous one, you can see we've got 1,393 bytes left. So that's not too bad. But when I go back and run this other sketch that we've just done now, let's go back to 3A. And if I upload this one, obviously it's a lot bigger because there's a lot more code. I've gone from 3.5K odd to 8K, so I've added quite a bit. But if I run this, once it's finished uploading, you're going to see how it works for a start off, but you're also going to see how much memory this thing is taking. So there's our little extended welcome screen. So if I just say hello again, alright, now we're down to 693. We've chewed up a huge amount of RAM, and we haven't added any extra buffers or anything. And what's really happening here is that when you run a sketch, it's actually typical for C, not just on an Arduino, any string variables that have been declared, so where we're doing all the struct comps and we're doing responses for the web and things like that, when the program starts, they all get copied into RAM because they're strings, and it's assuming you're going to do something with them. It's not just leaving them in the program space. So the more of that you put in there, the more space it's going to take up. And of course that's not very good. I mean, you've seen here we're already down to 693. Now I know that if I added an SD card library, that's going to take 500 bytes right off the bat, because the minimum block of data you can read off of an SD card is 512 bytes. Basically think of a floppy disk or something old school where the sector size was 512 bytes. The same thing applies to an SD card. So that's 693 bytes, which is just a snapshot of the memory, is going to end up being 193 bytes or less. And that's before you even do anything with an SD card. So you can see that we got very little done here. If I add an SD card and start trying to use it, I can pretty much guarantee that this thing is going to be misbehaving, because it's going to be running out of memory, or RAM anyway. And the problem with an Arduino, which is fairly typical of microcontrollers, is when you run out of memory, it doesn't tell you that you've run out of memory. It simply starts overriding code and various other things and just starts doing very, very weird behavior. And that doesn't always happen immediately you run the program. It can actually happen maybe half an hour later. It just depends on what kind of commands and things like that you do with it, or if you send it a big string rather than a small one, that these things can happen. So anyway, suffice to say that 693 bytes of memory left is not a lot, considering we've got 2K, and the only thing we've set up in our code is our little buffer here, which is 50 bytes. Right? We do not have any other buffers or anything. We've deliberately used defines, which don't take up any memory. We proved that before already, and we just simply got extra code. Right? But all of these things here, they're being put into RAM and they're taking up space. Right. So how do we avoid this? How do we, we've not got to the point of blowing memory or anything, but we're getting close. You can see how very, very quickly you can increase this. So enough of this particular sketch now. I've already uploaded it onto lesson 3A blog entry, so hopefully you've already looked at it and you're familiar with it. So now we're going to go on and we're going to look at the 3B sketch to see what changes I've made and how much of an improvement